Hello! In this video, we'll start working with NLTK, Natural Language Toolkit, which is a comprehensive Python library for natural language processing and text analytics. Originally designed for teaching, it has been adopted in industry for research and development and is often used for rapid prototyping of text processing programs and can even be used in production applications. Our first topic is the basics of tokenizing text. So let us first define a few fundamental concepts. Tokenization is a method of breaking up a piece of text into many pieces, such as sentences and words. That means that tokenization is the process of splitting a string into a list of pieces or tokens. A token is a piece of a whole, so a word is a token in a sentence and a sentence is a token in a paragraph. A corpus is a collection of text documents. Corpora is just the plural of corpus, which comes from the Latin word for body, in this case a body of text. So a custom corpus is just a bunch of text files in a directory, often alongside many other directories of text files. Let's see an example of how we can create our own text corpus and how can we tokenize it. So let's first start with the import of some packages in Python and with some functions to be used later. Here is the essential part. So we should have some kind of textual data in a file. So here I have a CSV file that contains Trump's posts from social media from the last elections in 2016. You can see here how this file looks like. Here we have the named columns, and then I'm only interested in this message column, which is basically text of a particular post. I want to extract these. And my goal is how to make a list of all words from these posts. Okay, so first I will drop out any row with missing data, and then I will extract this message column. Okay, so when we execute this, we can then turn this column into a list. So we can see how it looks like. So we have here a list with these posts as strings into the list. We can see it contains some of the posts contain URLs, some of the posts contains hashtags, and also some of the posts contain more than one sentence. So we can first remove URLs from our data set, and then we can turn all the letters into a lowercase. And we're pretty close now. If we see now this data structure, we can see that we have already obtained a list of lists, where each list in this list of posts contains words from one post. So we are pretty close. We just want to merge all these words into a one list. So to do that, we'll use this chain function. This chain function makes an iterator that returns elements from the first iterable until it is exhausted, and then it proceeds to the next iterable until all of the iterables are exhausted. It is used for treating consecutive sequences as a single sequence. And an argument contains a star at the beginning. We need to put a star in order to unpack every element of this list. So when we execute this command, we should get what we wanted. So the word list should contain a list of all words from our posts, Yeah, it looks so. So it is a pretty big list. So this is the size, more than 70,000 words. And another typical pre-processing step is to remove stop words from our data set. So we'll remove stop words. In case you haven't seen these stop words, the typical grammatical words that actually doesn't change much the meaning of our sentences. So with this command, we'll keep only the words different from the stop words. So if we see our word list now, we can notice it's now smaller. It contains about 10,000 words. So we got what we wanted. We tokenized our text corpus, and we can play around with the words. For example, we can see the vocabulary. If we run this command, if we make a set out of this list, we are basically picking up the original items from our list. So if we run this, we'll see that our vocabulary has this much is much smaller than our word list. So we can, this command will print out the length of our dictionary. We can see it sorted, for example. Okay, so we can see that we have also kept some numbers in our word list. And we can further explore, for example, lexical diversity. Lexical diversity is a measure of the lexical richness of the text. It shows the number of distinct words. If we turn to this code, we can see that basically it is the ratio of the size of the vocabulary to the total size of our word list. Okay, we can further explore, play around with our word list. For example, we can get an insight into frequency distributions of words. Frequency distribution tells us the frequency of each vocabulary item in the text. It is a distribution because it tells us how the total number of word tokens in text are distributed across the vocabulary items. And since we often need frequency distributions in language processing, NLTK provides some built-in support for them. And if we run this code, we'll get this frequency distribution. We can see, for example, the most common 30 words with a frequency. So here are some words with how much they appeared in the set. We can plot it also, or we can explore words based on their lengths. For example, this command will print out the words with the length more than 7 characters and with frequency distribution more than 7. So if we, for example, run this command, we'll get these long and frequent words.
Many linguistic processing tasks involve pattern matching to find certain patterns in text that are often more complex than a simple match against a sequence of characters. The most general widespread notation for such matches is regular expressions, which can describe patterns that are regular language, the kind that can be recognized by a finite state machine. Regular expressions give us a more powerful and flexible method for describing the character patterns we are interested in. Here is a list of operators that we can use in regular expressions. The dot symbol is a wildcard, so it matches any single character. Caret symbol is used to match some pattern at the start of a string, and a dollar sign is used to match some pattern at the end of a string. Square brackets are used to match one of a set of characters. The minus symbol in square brackets is used for ranges. The bar is used for disjunction, so to match one of the specified strings. Cleany operators are used for counting. So star indicates 0 or more of the previous item, and a plus indicates 1 or more of previous item. Question mark indicates 0 or 1 of the previous item. Curly braces are specifying countings, so the lower bound is indicated by the first number and the upper bound is indicated with the second number. Round parentheses indicate the scope of the operators.
Let's explore Outram dataset with some regular expressions. So we have imported the RE package, so we can use this search command. Search command searches for a particular pattern in a word, and we iterate. This loop iterates over our vocabulary V, and for each word it checks whether it satisfies the desired pattern. So for example, here we're interested in words that end with able. So if we run this command, we'll get a set of words. To be exact, we'll get a list of words like viewable, deplorable, round table, and so on. Another example of a regular expression is that we're interested in words that begin with letter B and with a letter S, and in between there are 3 dots, which is a wildcard symbol, so this will match any 3 characters in between these 2 letters. So if we run it, we get these 3 words. Another regular expression is inspired by T9 system, which is used for entering text on mobile phones. 2 or more words that are entered with the same sequence of keystrokes are known as textonyms. For example, both whole and golf are entered by pressing the sequence 4653. So if we run this command, we'll get gold and golf. Our next pattern uses cleany operator plus. Specifically, this pattern searches for words that begin with 1 or more M's and that end with 1 or more E's. If we run this command, we got only word mine. Our next command explores numbers. So with this operator, curly braces, we specify that we are interested in sequences of exactly 4 numbers. So if we run this, we get a list of 4-digit numbers. And our last example searches for words that end with ed or ing. So if we run this command, we got words like listening, light, stripped, balanced, indicating, and so on.
Here is a list of some special symbols that we can use within regular expressions. Many of them are useful because they're actually abbreviations of our more complex expressions. For example, instead of writing this, we write \d for any decimal digit, or any non-digital character we can write with \big D. Then, for any white space character, which is equivalent to this expression, we write \s. And for any non-white space character, which is this expression, we write \big S. Also, for any alphanumeric character, we write
\w. And for any non-alphanumeric character, which is this expression, we write simply backslash with big W. And also some commonly known characters such as character for tab and new line character. Okay, so let's go back to our remove URL function that we've used when analyzing Trump dataset. So we were calling it here when we wanted to remove URLs from each post. So the input parameter that we send to this function is a single post which contains one or more sentences, but basically is a string. So when we explore this function, it uses this function from RE package, a sub function. How the function works, basically it seeks for this pattern in a string. This is the input string, this is our post that we receive, and if it finds an example of this pattern, then it replaces it with this second argument, which in our case is nothing, because if we want to remove URLs. So if this is our pattern for URL, every URL will be removed because we will replace it with nothing. So how do we interpret this expression here? Actually, this second part at the right hand side of the bar operator is actually what a URL is. So basically we have one or more of a alphanumeric characters, which is followed by a column sign, and then we have these two slashes with a backslash we indicated is a special symbol. And after these two slashes, this backslash big S catches one or more non-space characters. So basically this will suffice to catch the total URL, and the alternative to this at the left hand side of the bar is basically, as we can see, a negation within a square brackets, which indicates non-alphanumeric, not a digit, not a letter, but also not a space, not a tab. So basically this will remove any weird symbol that appears within our post. For example, even including the hashtag symbol. So if we have a hashtag in our post, it will remove only the hashtag symbol, but the words following that hashtag symbol will remain in our post.
One of vocabulary reduction techniques is to normalize the vocabulary, so that tokens that mean similar things are combined into a single normalized form. Normalizing word and character capitalization is one way to reduce vocabulary size. It helps to consolidate words that are intended to mean the same thing and be spelled the same way under a single token. The simplest and most common way to normalize the case of a text string is to lowercase all the characters. Another common vocabulary normalization technique is to eliminate the small meaning differences of pluralization or possessive endings of words or even various verb forms. This normalization, identifying a common stem among various forms of a word, is called stemming. For example, the words housing and houses share the same stem, house. Stemming removes suffixes from words in an attempt to combine words with similar meaning together under a common stem. A stem isn't required to be a properly spelled word, but merely a token or label representing several possible spellings of a word. NLTK includes several off-the-shelf stemmers. The Porter and Lancaster stemmers follow their own rules for stripping affixes. Stemming is not a well-defined process, and we typically pick the stemmer that best suits the application we have in mind. The Porter stemmer is a good choice if you are indexing some texts and want to support search using alternative forms of words. In the slide, we can see an example of Python code using stemmers, and we can see some differences in these two stemmers. For example, the Porter stemmer correctly handles the word lying, mapping it to lie, while the Lancaster stemmer does not. If you have access to information about connections between the meanings of various words, you might be able to associate several words together, even if their spelling is quite different. This more extensive normalization, down to the semantic root of a word, its lemma is called lemmatization. An example of a lemmatizer is a NLTK WordNet lemmatizer, which only removes affixes if the resulting word is in its dictionary. To conclude, lemmatizers are better than stemmers for most applications. Stemmers are only really used in large-scale information retrieval applications.